the back. Oops. I'll let Chris do it. Is it recording?
Yes.
Okay. All right. So I said I would have a simplified way to tell you how to determine the induced current direction, and so that's what we're going to do with Lenz's law. So we're going to look at this picture down here first to kind of introduce the concept, and then we'll kind of simplify it once we understand this picture. So if you've got a coil of wire with current flowing in it, like you guys did last week, it creates its own B field. And if your current is flowing around like this, in this picture, that's going to create a B field that's to the right inside that loop. That's what you guys detected in your experiment last week. You could imagine that that B field is the same B field of an imaginary magnet, right? So if you imagine a north-south bar magnet that has the same B field as your wire, let's just do that for now. So if you introduce another magnet towards your current carrying loop, and that magnet has its north face on the same side as your sort of imaginary magnet that you're creating with your current carrying wire, the north sides of those magnets are going to repel. So the B fields are in opposite directions. But let's say you pull that bar magnet towards your current carrying loop anyway. Let's see. Okay, so oh man, I got to read what I did here. I'm confusing myself. Okay, I introduced it wrong. Let me start over again. Let me explain this picture again. All right, so just erase your memory for a second. All right, now you've got a loop of wire that you are not driving current through. So this is similar to what you did last week, but a little different. So you've got this loop of wire, you're not driving current through it, but you take a magnet and you push the magnet into it, the north side of the magnet going into it. So the B field from that bar magnet is into it. Lenz's law says that an induced B field will be created in that loop, and thus an induced current will be created in that loop to oppose the incoming field lines. So the idea here with Lenz's law is it's always trying to oppose change. So if you're increasing the B field, it's going to create a B field, an induced B field, to oppose it. But if you already have an established B field and you try taking it away, then it's going to create an induced B field to try and keep the B field at the level that it was already at. So Lenz's law is all about just being really ornery and contradictory. So if you've got this incoming B field to the left, then you're going to get an induced B field to the right that's opposing that B field. And so our induced B field, B sub I, is going to create an induced current using our right-hand rule that shows that current going down on the outside and then up on the inside. So that's the direction of the induced current. And this can get a little confusing because we have our external B field and we have our internal induced B field, and we have an induced current. So we've got lots of loops to practice on. And here's every possible situation that you could have. So over there on the far right or far left, we've got the same situation we just talked about. So the north side of a magnet is going towards a loop. There's going to be an induced B field to oppose that incoming B field. That induced B field creates a current that's flowing counterclockwise around that loop. That's picture A. Another view of that, I'm going to draw my incoming, my external B field in blue. So if I've got an external B field that's going into the board and increasing. So external B field is increasing in loop. Then we get an induced B field equal and opposite to that. So B sub I, induced B field, so it's opposite the external B field to oppose the change in magnetic field. And so our induced current is based on the induced B field direction. So to match up our colors so we don't get confused, I'm going to use red for my induced current. So you can see there's areas to make mistakes, because if you use the external B field, that would give you the wrong answer. So that's why I'm using red and red to associate the induced B field to the induced current. Okay, so we can have the same bar magnet with the B field going into the board like we had in the above situation, but let's say it's been sitting here a while and then we pull that magnet out. So B external is decreasing in the loop. So based on what I've said about Lenz's law, what direction is the induced current going to be if we have a decreasing external B field? Not the current. What's the direction of the induced B field?
Out of the board.
Out of the board? Just like this case? Into the board?
Into the board.
Into the board? So why, a couple more people said into the board. Why do you guys say into the board?
Well, if you're pulling that one out, it would be opposite, so try to keep it back in.
Try and keep it the way it was? Yeah, so just keep everything status quo. So to keep it status quo, it's going to add to the loss of B field. It's feeling a loss, so it's overcompensating. Okay, so we get a B induced B field that's in same direction. Again, because it's trying to oppose change. Okay, so if that's the direction of your induced B field, what's the direction of your induced current?
Clockwise.
Clockwise? Jan says clockwise. Chris says clockwise. So I put my thumb in the direction of the induced B field, my fingers then curl around the loop, and they're going clockwise. Yeah, so I can even write that. Clockwise is how we write CW for clockwise. This case would be counterclockwise. So you can use that notation on your notes if you're saying whether a current's going clockwise or counterclockwise. Okay, so we've got two more cases here where we can have the B field, external B field coming out of the board. So B external, and we're going to say it's increasing in this case. And, oops, this one's also coming out of the board. And this case is decreasing. So does anyone want to volunteer to draw the direction of the induced B field and the induced current on this one? Jordan? Yeah?
The induced current, is there going to be another current of that is, sorry, so is the external causing a current as well?
It's causing the induced current.
Okay.
Yeah.
So the induced current would be the total current. There wouldn't be a net.
No, I mean, if you had it connected to a power source, you could add your own current too. That would complicate things for sure. So you could have like an external current and do all this with external currents, they would also create induced B fields. If you had a B field, it gets very complicated.
Okay. I was just thinking, like, if the blue, the external, the blue created a current, it would be in the opposite direction.
Well, the current that it is creating is the induced current.
Okay.
Yeah, but we figured it out based on the induced B field direction. But ultimately, the only reason we have an induced current is because we've got a changing external B field.
Okay.
Yeah. Yeah, Chris?
Does this only work as would it be called an inductor, that magnet?
Yes.
Okay.
Yeah, I mean, the whole thing is an inductor.
The whole thing is an inductor.
Yeah.
Okay. So as the magnet is moving closer and closer to the loop, current is being inducted because of the induced magnetic field that is opposing the change.
Uh-huh.
So does it only work as it's on one side and you're kind of moving it in and out, or what happens when you move it past the plane of the center of the circle? And suddenly the magnetic field is on the other side.
It would, I mean, in terms of magnetic field lines, as it's approaching the center, your B field is increasing.
Right.
And so say this is your loop. So if the B field's increasing, you've got an induced B field opposite to that.
Right.
So your current would be going this way. As soon as it crosses a center line, now your B field is decreasing. So your induced B field's in the same direction. And so your current would now be going in the opposite direction.
Trying to resist that change.
Yeah, so if your magnet went back and forth through the loop, it would just cause the current to flip.
Alternate.
Yeah.
Cool.
So that's how you can create AC current. So yeah, works pretty well. All right, so what do you guys think about Jordan's attempt at this? Did he get it right? Okay, so we've got our increasing external B field, so we've got an opposite induced B field. The induced B field creates an induced current that's clockwise. Does someone else want to take a stab at the bottom one? Chris, go ahead.
Yeah, I was thinking about the induced magnetic field opposing. Actually, it makes a lot of sense when you think about the work energy theorem. If you're having an inductor that's basically taking mechanical energy and converting it to electrical energy, you have to be putting work into the system. And in order to do that, you have to be, I guess, fighting some resistance, some negative work to put work in. So if it didn't oppose, then you wouldn't be putting any work into the system. It has to be opposing so that you are putting work into the system. It's like
You can't get free energy.
Yeah, you have to push the cart up the hill to build up that potential energy, put energy into the system.
Yeah.
To do work to push it uphill. If you didn't do that, you wouldn't be putting any work into the system or energy into the system.
Yeah. So it's sort of creating a stored energy that you can then utilize. Well, that's a really great way of looking at it. All right, how did Chris do? You guys agree? Okay, cool. All right, so these pictures are all what we've just done, so it's just a reiteration. All right, so that's induced current. That's how we get induced current. And then induced current leads us to getting induced EMF. And so the definition of EMF, again, we recall that it was a really weird word that they misnamed, but it had to do with work. So EMF was work done per unit charge to produce a current, AKA it's a voltage. It's like a battery. Okay, so we use the symbol, what did we decide it was called? Psi? Yeah. Loopy E, for those of us who are not so sure about how to say it.
Like an East Coast rapper.
Psi.
No, Loopy E.
Oh, Loopy E. Okay, well, Psy kind of sounds like a South Korean rapper. Psy is awesome. Okay, so Faraday's law is sort of neighbor to Lenz's law. They're really friendly. Faraday's law says that an EMF is induced in a loop when the number of field lines through a loop is changing. And so that was really kind of what Lenz's law said about induced current. It said we get an induced current if the B field is changing. Well, now we get an induced EMF if the B field is changing. So I think Faraday's law and Lenz's law should get married. Okay, so EMF, this is all related to flux. This is all related to flux. So we said flux is the amount of B field flowing through your wire. So if your B field is changing, you've got a changing flux. So in all these situations, we have a changing flux. And so it makes sense that our EMF can be written in terms of a changing flux. And that's exactly, it's a very simple definition. And these boxes that look nice and bright and yellow to me look really dark to you guys. Is that better? Slightly better. Okay. I think I need to stop making my boxes bright and yellow because they just never look that bright to you guys. Okay, so our induced EMF is negative to the change in flux. So that's just very simple explanation. The negative sign is one of those suggested negatives. We don't always apply it, but it's basically a reminder that the EMF opposes the change in B field. So that was just like our induced B field. It opposed the change in the external B field. And so an induced EMF, same thing goes. You're not always going to need the negative sign. So just keep that in mind. And we said in some cases we can simplify our flux equation to just B times A. And so this is the simplified version where you get rid of your negative sign and you're just saying the flux is B times A and you're taking the time derivative of that. So this isn't always going to work, but in some of those cases it will work. So my little reminder about this, size doesn't matter. The strength of the B field doesn't actually matter. It's how much the B field is changing that matters. So some ways for our flux to change through our area. You could change the B field. So you could do that by moving your magnet, or if you have an electromagnet, changing the current. That electromagnet will just change the B field value. You could take a loop that's got sort of like a loop of wire that's got two arms on either side sticking out, and if you pull it, that would shrink the loop. Or you could push it together and grow the loop. So if you change the amount of field lines that can go through your area, you're going to increase your flux or decrease your flux. So that's another way for your flux to change. Or you can take your loop and in these pictures, you could just rotate it. That's gonna, you can maximize the flux through the loop or you can minimize the flux through the loop. And like our pictures over here, usually you've got more than one loop, so you just throw an N out front and your EMF is multiplied by the number of loops you have. Okay, so now we've got a couple equations to work with. I'll add our induced EMF equation to the board. Okay, so let's look at example 29.1 to start, and problem 29.2 if you zip through example 29.1. So try these out in your groups, talking about them first, and we can come together as a class and talk about them after people have had a little bit of time to try them on their own. All right.